Thank you very much, Mr. Chairman. So my name is Raul Campilho. I come from ISDEP Engineering in Portugal, and in this work we are addressing the optimization of a margin steel 1.2709 by the SLM process. And here we can check the structure of this presentation, which will be mainly divided into four parts: the introduction, materials and methods, results and discussion, and conclusion. And we emphasize the results and discussion. We are going to evaluate the optimal conditions of this alloy by different types of tests: relative density, porosity analysis, roughness, harshness without and with heat treatment, and finally tensile characterization by both testing. A short motivation to this work. So we know that additive manufacturing is widely used currently. It's based on the sequential addition of layers, which eliminates the need for molds and specific tools and allows to create very complex geometry parts. In this process, selective laser melting, in particular, it is widely used to produce metallic parts that needs to have high density and elevated mechanical properties when compared to manufacturing processes. The alloy steel, such as the one that we are addressing today, the 12709, they have specific challenges in the fabrication related, for example, to residual porosities, high surface roughness, and anisotropy, which can compromise their performance. Since this alloy in particular is widely used, it is relevant and important to optimize the fabrication parameters and investigate the processing conditions so that we can reach to the best properties possible. In view of this, the main goal of this work is to analyze the influence of the parameters of the process and the heat treatment on the properties of this maraging steel to identify the best conditions in terms of density, mechanical strength, and surface quality. With this in mind, we have specific objectives. Mainly, we want to evaluate the VED, the volumetric energy density, and also different scanning strategies in the fabrication, set board and stripe, on all of these parameters. Here we can see the characteristics of this material, of this maraging steel, which has as alloy elements nickel, cobalt, molybdenum, and titanium in the percentages that are presented here in this part to the right. We have a composition that ensures a martensitic matrix, but this can be strengthened and modified by aging treatment, which is one of the focuses of our work to evaluate the influence of this type of heat treatment. Beginning with the experimental part of the work, this work was carried out in a Trump 2Print 1000 basic edition printer. In terms of parameter combination, we considered two extreme conditions. One of these is the reference properties provided by the manufacturer, which leads to a VD of 96 joule per cubic millimeter, and the machine limit of the power in terms of speed and power, which leads us to a smaller VD, which is about 27 joule per cubic millimeter. And between these conditions, which are the ones in this table, we are also going to consider intermediate combinations to cover a higher range of parameters. As it was said, we considered two printing strategies or two scanning strategies, chessboard and stripe. We kept the layer thickness and the hat space constant, and with these conditions, we reached to this plan of test, half of the specimen which board and the other half with stripes, so that we could analyze the influence of this parameter. And all of this with and without heat treatment. In this slide, we can see some details about the testing plan and the fabrication of the specimen. We fabricated two types of specimens. First, we have cubic specimens for the density, roughness, and hardness test. We can see here one set of specimens being printed, and we have also tensile testing specimens, which are both backbone specimens used for tensile testing. In terms of heat treatment, we evaluate the heating by precipitation of the intermetallic phases, aiming to increase the hardness and the strength. We have the cycle, we have a 5-hour cycle at about 500 degrees, and we want to evaluate the effect of this precipitation hardening on the marathon steel that we are evaluating. In terms of results, and beginning with the relative density, we can compare the density without and with heat treatment. In blue, we have without, and in orange, we have with heat treatment for the different VEDs and for the two types of planning patterns. And we concluded with this first test that higher VED leads to a near full densification, so almost 100% density, while the lower values of VED show a significant porosity, which reflects in a smaller relative density. Between the fastboard and stripe strategies, we have almost always a similar trend, but fastboard usually leads us to slightly higher relative density. On the other hand, the heat treatment it gives us a significant increase in the relative density, as you can see, especially with the smaller V applied to the specimen. In terms of porosity analysis, and beginning with the influence of the VED, at the highest VED, we can see in this micrograph that we have almost no porosity, which confirms that we have a good and good consolidation. But as we increase the VED, and especially in these two configurations of 20 and 26, we have a much more evident porosity and large zones that are unmelted and lack of fusion. By comparing the two different scanning strategies, both of these have the similar trend, which means that we have reduced porosity with higher VED and lower porosity and lower VED with increasing porosity, but we can see that we have a slightly better porosity distribution with the fastboard strategy compared to the stripe strategy. In terms of roughness, we measured it in different planes, in the cubic samples, in different planes. We can see that the roughness typically increases with the reduction of the VED. So as we go from left to right in this plot, the highest roughnesses were found for a VED of 40 joules per cubic millimeter, while the best results were found for the highest VED considered of 96. And between the two strategies, we have a slightly roughness for the stripe strategy, which means that the fastboard is better result to a higher homogeneous heat distribution during. In terms of hardness, before heat treatment, the hardness decreases with smaller VED because we have higher porosity. We have the maximum hardness of about 400 Vickers at 96 VED, while we have much smaller values, about 140 per cubic millimeter. Once again, comparing the fastboard with the stripes, we can see that we have higher hardness with the fastboard because of the considered more uniform cooling history. Now, if we compare the hardness after the heat treatment, we can see that this treatment significantly increases the hardness in all of the conditions. These are the two columns to the right in each set of. So we have an increase which represents in some cases up to 50% of gain in the hardness, And this is because of the uniform increase uh, promoting of the heat treatment in terms of hardness and comparing the testboard strategy with the track strategy, we have slightly higher values for the testboard, which confirms again what we saw in the last slide, that we have a more uniform thermal history in the case of applying testboard scanning during the fabrication. In terms of tensile data, here we can see the stress strain curve for VED of 26.7 and the stripe scanning pattern. We don't have significant differences in the data, in the maximum force and in the stress at break. So here there is no significant difference between before and after the heat treatment. The board has slightly higher differences. For example, in the stress at break, we have an increase of almost 50% in the stress at break, but the best results were obtained by a VED of 96 for the test board, in which we have much higher stresses at break. We have an increase of almost 100% between before and after heat treatment, but to the expense of a reduction of the ductility of the specimen. And here we can conclude this work. The main purpose was to reach to the best parameters, and here we can see the best printing parameters that give us the best results in terms of relative density, in terms of surface roughness, and in terms of hardness, which is about 400 Vickers before heat treatment or almost 600 Vickers after heat treatment. And finally, for the tensile test, by applying the heat treatment, we had major increases in the yield strength and ultimate tensile strength, but at the expense of a reduction of almost 80% in the ductility. Finally, the conclusion for future work, and thank you so much for your attention, and please tell me if you have any questions.